Hey, welcome to another episode of Earth is Our Home with Dr. Tom Blaine. Today, we're going to be talking about the Coriolis Effect Part 2. So stay tuned. Welcome back to another episode of Earth is Our Home with Dr. Thomas Blaine. He is an associate professor with the Ohio State University Extension Program. And we're going to be talking about Coriolis Effect Part 2. Tom learned a lot from Part 1, and I'm hoping that you will continue to help me to better understand what the Coriolis Effect is.
It's my pleasure, Patrick. The Coriolis Effect is extremely important. It's a major factor in determining our weather, our climate. You just can't understand weather patterns without understanding the Coriolis effect and the spin that it puts on airflow and water. And some people misunderstand it. We went over a little bit of a myth about it last time, and we're going to do that again today, make it a little bit fun too. Okay, so this is Earth is Our Home is the series. Here we are in July 2021. This is part 11. And so far in Earth is Our Home, there are many environmental topics to discuss, but we are still on Earth's climate because the topic of climate change is so important. And there are so many factors that contribute to an understanding of climate that we have decided to go through as many of these kinds of important factors as we can. And we started last time on the Coriolis effect. And as I told you then, we wouldn't be able to get through it all then. So this is part 2. And remember, it's not a force. Now, you hear the term Coriolis force. And if you look down, let's skip down to the bottom. A lot of people say Coriolis force. It's technically not a force. Gravity is a force. You climb up a tree, you jump. That gravity, it's like invisible fingers snatching you down toward the planet. It's a true force. It keeps the Earth in orbit around the sun and does all kinds of things like that. It's a force. The Coriolis effect is an apparent force. It looks like something is acting that's a force, but it's not. It's an effect of the spinning or the rotation of a spherical object, in this case, the Earth. It causes winds in the northern hemisphere to swerve to the right, and it causes winds in the southern hemisphere to swerve to the left. And so we're going to go through that again a little bit today. I am going to ask that we post down below today's video the link to the last video that we did last week on Coriolis Part 1, so that if you want to go back and watch that first, you can. The Earth rotates one rotation a day, every day, no matter where you are on the Earth. If you're at the equator, the Earth rotates all the way around and facing the same direction a day later, 24 hours later, as it was when that particular rotation began. And that's the same in Ohio. It's like that in Greenland, But the thing about it is the circumference of the Earth is greater at the equator. It's 24,000 miles around the Earth at the equator. It's only about half that by the time you get to 60 degrees latitude. Think about the geography of the Earth. And we've shown plenty of globes for you to look at. And I think that people understand that the Earth does get smaller in circumference as you leave the equator and go toward the poles. But what that means is the Earth has to spin faster to make it the 24,000 miles. It's got to spin faster at the equator than it does in Ohio, where it's only roughly, I believe, about 18,000 miles, or at 60 degrees latitude, where it's only about 12,000 miles. The spin at 60 degrees latitude is about 500 miles an hour, half as fast. And so, because of the various rates of spin and the rates getting smaller as you go toward the poles, it creates some pretty strange effects that we're going to talk about here. So last time we focused on how it forces things to swerve to the right in the northern hemisphere. So now we're going to do the southern hemisphere. Winds and other items in the atmosphere swerve to the left in the southern hemisphere. So I'm going to ask you to imagine you're on the continent of Antarctica and you throw a ball north towards, say, the tiny country of Uruguay. Uruguay is between Brazil and Argentina on the east coast of South America. Let's look at that peninsula. We're looking straight down on the South Pole. If you look to the left, like towards South America, you'll see there's a pretty long peninsula out there. Let's say you're just a little ways from the main part of Antarctica out just on the peninsula due south of Uruguay. And you can see Uruguay on the east coast of South America. See it written there between Brazil and Argentina. Very tiny. It's purple there. So we're going to throw a ball from that peninsula toward Uruguay. The thing about it is the peninsula, Uruguay, everything is spinning one full spin, one rotation a day. But as you can see, the distance around is much smaller where that peninsula is compared to where Uruguay is. So the spin is faster at Uruguay than it is at the peninsula. So what happens is you throw the ball as it's moving, Uruguay is spinning faster, which makes the ball move to the left, going behind, because the Earth is rotating, as we know, from west to east. And by the time the ball gets up there, it will be out over Chile on the west coast of South America, or maybe it'll be in the ocean. Now let's imagine the other way around. Let's say we're standing in Uruguay and we're going to throw it back. What we're going to do, we're going to throw the ball from Uruguay down to Antarctica this time. So let's say you're standing there in that little purple between Brazil and Argentina, and you want to toss that ball down to the peninsula. All right. The thing about it is at Uruguay, you're spinning a lot faster than the peninsula is, and you're spinning in the direction of Africa. The entire Earth is moving from west to east. And so when you throw that ball, it's going to have the motion on it that causes the ball not to go straight toward the peninsula, but actually to the left from where you've thrown it. So we're looking from the pole here. And, just like when I'm facing you, your left is my right, and my right is your left. It's going to cause that ball to move away from the peninsula and toward that large bay. If you see the bay to the east of the peninsula, or toward where it says Southern Ocean, right? Okay, so standing there from Uruguay, that's going to be to the left. It's going to cause the ball to land there in the Southern Ocean and not at the peninsula. It's going to swerve to the left. So let's talk about that a little bit. The ball appears to move out ahead because it's moving from an area of rapid spin, fast rotation. The Earth has to go faster because one rotation per day, and it's a bigger circumference at Uruguay than it is on Antarctica, moving into one of slow spin. So that means it veers to the left. or to the east from the position where it was thrown in this case. Now, this is what happens to winds. All right. It's not so much about throwing balls. It's really an example to show you what happens to winds. They veer to the left in the southern hemisphere, which means winds that are traveling south veer to the east. Winds traveling north veer to the west. And lo and behold, remember our global climate circulation? It turns out we've been using this one a lot to help us out. If you go down to South America, it just so happens that one of the arrows they chose, the line leading to the arrow starts right at Uruguay. And it's near where it says 30 degrees south latitude there in eastern South America. And remember, we were going to throw a ball toward that peninsula. And if you go straight south of Uruguay, and again, that's the area where that red is starting, that's moving south. You go south of there and you can see the peninsula jutting out that we talked about there on Antarctica. So the wind pattern here is exactly like our ball example. The wind started out moving toward the peninsula. You can see it. But because of Coriolis, it veers east, which is to the left from the direction of which the wind is coming. It is moving to the east, which is to the left. If you were in Uruguay, and it appears on our perspective because we're looking in the opposite direction, that it's moving to the right. All right. But in any case, it's moving to the east. And that's the Coriolis effect. And that's causing the prevailing westerlies in the southern hemisphere. Remember, we live between 30 and 60 degrees in the northern hemisphere. We have prevailing westerlies also, but they're coming up from the south and then hook around to the right, which means they come out of the west. Prevailing westerlies here in a feral cell in the northern hemisphere, prevailing westerlies in the southern hemisphere are also in a feral cell. I want to talk a little bit about how this works in terms of high and low pressure systems. So we've talked before about a high pressure system and what it is. High pressure, you got sinking air and it's pushing out. It's wanting to push out. The pressure is high. Okay. Imagine something with high pressure inside of it. It's pushing and wanting to get out. The thing about it is, in the northern hemisphere, when that air leaves the high pressure system, it can't go straight. It can't go straight. It can't just move away from the high pressure system. Why? Because of the Coriolis effect. It's bent around to the right. That means winds blow clockwise around a high pressure system. All right. And because air moves away from a high pressure system, because all that pressure is pushing, it tends to move away. But we know it can't just move in a straight line away because of the Coriolis effect. So whereas here in the northern hemisphere, as we talked last time, winds swerve to the right because of Coriolis. We have in the northern hemisphere, high pressure circulation is clockwise. In the southern hemisphere, high pressure, you have circulation counterclockwise around the high pressure and clockwise around the low pressure. Just the opposite of what we have in the northern hemisphere. So what are the implications of this for storms and things like that? I want to shift and talk a little bit about hurricanes. Hurricanes are not very common at all in the southern hemisphere. You know, we get into hurricane season about July, August, September. That's the peak of hurricane season here in the northern hemisphere. There are many, many more hurricanes. Typhoons are the same. They just happen in the Western Pacific as you get toward the Philippines and so forth. They're called typhoons. Very same phenomenon. And sometimes in the Indian Ocean, they're called cyclones, but they're the same phenomenon. They are a giant low pressure system, a huge storm that's fueled by the very warm water of an ocean or a sea. You've got to have very large amounts of very warm water to set the hurricane in motion. And once you do that, if you do get a hurricane in the southern hemisphere, it's going to rotate clockwise because it's a low pressure system. However, there aren't many down there. It's very rare. In the northern hemisphere, as you probably are aware, we have a lot of hurricanes. And here we have hurricanes rotating in a counterclockwise direction. Now, a lot of people ask, why are there so few hurricanes, typhoons, cyclones in the southern hemisphere? Why? After all, there's a lot more ocean in the southern hemisphere, a lot more room for them to begin. Why didn't it happen? Well, remember we talked a lot before about how positions of continents make a lot of difference. The prominence of Antarctica, a continent right at the pole, means that waters throughout the southern hemisphere are going to come in contact with water that is in proximity to Antarctica. And this cools the waters of the southern hemisphere. So generally speaking, the waters of the southern hemisphere don't have enough heat energy to get a hurricane going. Hurricane is a lot of energy being released. And in order to have that, you've got to have a lot of heat on the surface of the ocean. Again, that's why our hurricane season in the Atlantic, the Gulf of Mexico, the Caribbean tends to peak in August and September, because all summer long, the sun's been beating down on that, heating that water up. A lot more heat energy on the surface of the ocean in that region in August and September than in April, May, and June. That's why we don't get very many hurricanes there in April, May, and June. The big portion of hurricane season, when everybody's glued to their TV, is in August and September. And so, again, the way the continents are arrayed, the way ocean currents work, plays a huge role on climate. I can't emphasize that enough. And seeing is believing. If you've seen what hurricanes do to these tropical places or to the state of Florida or the Carolinas, the devastation, and then you look and think they never hit Brazil. Brazil's a tropical country. They never hit down there at Uruguay. And yet it's right on the Atlantic Ocean, but they don't get hurricanes. Southern Africa, a lot of ocean, no hurricanes. It's because of these impacts of the continent locations and the ocean currents. Okay, and this is what I'm talking about. Picture tells 1,000 words, right? This is an image of a hurricane. And if it scares you to look at this, congratulations, welcome to the club. If you look carefully, you don't have to have a lot of weather background to realize this hurricane is spiraling counterclockwise. We know that low pressure systems spiral counterclockwise in the northern hemisphere. This hurricane is right off the coast of Florida, northern hemisphere. You can see by the way the storm bands are, even without this being in motion, that it's rotating counterclockwise. You see those arm bands down there that start way out at the Florida Keys and go south of Florida and then come on around. They're being pulled right all the way around. And it's like a giant vortex. The winds are trying to get into the center of the storm where the low pressure is, but they can't make it in there. And you should know by now the reason. It's very low pressure. Winds want to go to low pressure to equalize the pressure, but they're guided around. They can't get in there. They spiral and build into a massive storm that floods and kills. Why? Because of the Coriolis effect. Because the spinning of the earth forces that air to go around counterclockwise. Low pressure, northern hemisphere, counterclockwise flow. If we didn't have that, the wind could rush in, equalize the pressure. There wouldn't be a hurricane. But because of all these phenomena, all these facts, hurricanes exist. And just to read that, the darker the red, the stronger the storm. You notice typically in a hurricane, the strongest winds are pretty close to the eye. This hurricane is showing extremely strong winds to the northwest of the eye, to the west, to the southwest, the real dark red. But even outside in the spiral arms, way down south of the main body of the hurricane, some of that outflow has led to enormously strong winds, those dark red, and then light red and orange are weaker, then green, and then yellow, and then we get to blue where it is relatively calm. So we did want to come back. It's flowing like that, counterclockwise here. If you do have a hurricane, which there are some in the southern hemisphere, they rotate clockwise. So is it true water flows down the drain differently in the northern versus southern hemisphere? No, it's not true, because the Coriolis effect does not operate to a visible degree on a small scale like a sink or a bathtub or a swimming pool. It's a macro phenomenon. Hurricanes are hundreds of miles wide. And so the Coriolis effect acts on that. I was giving you examples from Uruguay to Antarctica. Okay, that's across continents, right? And last time we did Minnesota to Louisiana. Those were long distances. In order for the Coriolis effect to work to a degree that we can observe it, it's got to be on a macro scale, like the tides. The Atlantic Ocean, if you go to the beach, there are tides. You go out there and the water's way up. 4 hours later, it's a big beach because the gravity, mainly from the moon, is pulling, right? It's pulling, but there's no tides on the Great Lakes as big as they are because the Great Lakes are not big enough to have tidal effects. The effects just are simply not observable. And so the Coriolis, people see all these spiralings of the storms on weather maps and so forth, and wonder about this. And there's an urban legend that it's true that it does that, but it's not true. It doesn't happen on that small of a scale. There's a difference between macro and micro phenomena, and we've talked about that before.
Last year, in the 2020, there were a lot of different hurricanes. There were more than the average year. What caused that?
Well, on average, there are 10 named storms in the Gulf, Caribbean, and Atlantic basin. This basin that we're looking at here, where Florida's pretty much the center. So think of that as one basin, the Gulf of Mexico, Caribbean Sea, and the Atlantic. That's one basin. There are 10 named storms. Now, you don't have to be a hurricane to get named. You have to become a tropical storm with top winds of about 39 miles an hour. Then you get a name. When you get to 75, you keep the name and you're now a hurricane. There are an average of 7 to 8 hurricanes in the basin a year, an average of 10 named storms. They vary each year because conditions vary. Sometimes the extent of warm water is greater, but it takes a lot of special ingredients for this to happen. For example, if you have wind shear in the atmosphere, and I think a lot of people have heard of wind shear. Wind shear is wind blowing at different directions at different elevations. So let's say you go up 500 feet in a balloon or something, and the wind is out of the west at 15 miles an hour. And then you go up to 1,000 feet and it's out of the east. That's wind shear. A hurricane can't develop in that. It'll just be ripped apart. Any big storm system that tries to develop gets ripped apart. So sometimes we talked about air currents and how some of it's kind of chaotic. One of the big differences from year to year could be the temperature of the water. If it's a little bit warmer there, it'll tend to spawn more hurricanes. That's why a lot of people are concerned that global warming will produce more hurricanes because we'll have more warm water. It'll be warmer longer. Hurricane season will be longer. There's some reason to believe that that's true. But another factor is wind shear. It's a huge factor, and wind shear is partly due to the chaotic nature of the atmosphere. Why winds? We talked about microclimates and how there are prevailing westerlies. There are the trade winds. They tend to go in those directions, but disturbances can move in and reverse the direction of the wind at certain elevations. And when it does that, you get wind shear. And when you get that, you're just not going to have it's not going to be a very active hurricane season as long as that wind shear lasts. That would be, I would think, the two major reasons why the numbers vary each year.
Hey, we're talking with Dr. Thomas Blaine. He is an associate professor with the Ohio State University Extension Program. And Tom, I really appreciate all the time and energy you put into these video series. I look forward to our next episode. And in the coming episodes, we're going to be looking at some of the claims that climate change has, and are they true or not? So stay tuned. Thank you, Tom.
Thank you, Patrick.